We know that Mars now is a very different place to what it used to be. So 3.8 billion years ago, Mars had water on the surface, it had volcanism, it had a magnetic field. It was very Earth-like, you know, a almost breathable environment, so very different. That is definitely about the time that life was developing on Earth. So we think there's a chance that life could have developed on Mars as well at that time. So what we're actually looking for is signs of that life from that time. And if there's signs of any life which is currently there on Mars, I think that is a lot less likely. But the more likely thing is that we'll find, hopefully, evidence of ancient life on Mars about 3.8 billion years ago. It's one of the oldest questions which we've had, you know, from looking at the night sky. Are we alone? You know, and it's a fundamental question which everybody would like to know the answer to, and we have a great chance of actually answering it.
So today we're at Mullard Space Science Lab for the annual PanCam Science Team meeting. So we're here for the day to learn about the latest progress and the status of things. Now conveniently we happen to have the PanCam emulator here, and we thought it would be a good opportunity to use it to get a picture of the science team. It's a particularly exciting meeting this time because all the hardware has now been delivered for the flight model.
PanCam, this is the scientific eyes of the Rosalind Franklin Rover.
It is the main camera on top of the ExoMars Rover mast.
The Panoramic Camera is two cameras that are spaced 500 millimeters apart.
Stereo imaging cameras of the WACs.
The WAC camera is built by Thales in Switzerland.
And they both take simultaneous images, and when you overlay the images you can get a 3D image.
You can actually creating what we call a depth map. We know what the distance is for each single object.
For stereo imaging and plotting of routes on the Martian surface, so looking at what's in front of the rover and working out where it can go.
The sensor is a monochrome sensor.
To enable the camera to capture different spectrum of the scene, then we have this photo wheel.
So we can move that around to look at the different colours of the light coming from the surface of Mars. And so with that we're able to not only build up a colour picture, but also to look at composition of the rocks, and to look particularly for water-rich minerals, because of course we're looking for water and life on Mars.
And then we've also got some solar filters as well, so you can look at the sun if you want to through the atmosphere.
And then we have a high-resolution camera.
This hole here is for the HRC.
The HRC camera is made by DRR and OHB in Germany.
We are designing the instrument together with an industrial partner. That's OHB in Munich. So I am working together with our German partner, but I'm also very closely working together here with MSSL, with our UK partners. You need to basically interact on a day-to-day basis. And so the relationship is very close. And it's also, we are not only working together on a professional basis, after all this year we are friends as well.
So the high resolution camera will image what we get into the sample drawer, which is then taken into the main body of the ExoMars rover, looking for signs of life and biological traces and things like that.
And then we are also tasked to acquire images of otherwise inaccessible locations for the rover, places where the rover can't go, for example, on steep slopes in crater walls or in valley walls, and this might be tens of meters away. So this camera needs to take focused high-resolution images of very close targets and very far away targets, and for this you need an adjustable focus. You might think that's actually not difficult because every consumer camera has that, but to build something like this in a way that it's robust enough for Mars is not so easy. That was actually quite tricky.
We deliver the instrument as a whole, which includes the optical bench and some calibration markers.
So there's been a lot of work done on pre-flight calibration, but when we get there we really need to understand the colour of the Martian skylight in order to be able to process our images. And the best way of doing that is to take something with us which we know exactly what colour it is. So we have a radiometric calibration target. Mars is subjected to quite a lot of ultraviolet light, and that tends to bleach things, as you'll have noticed if you leave anything on your windowsill for any length of time. But we know that stained glass is very stable in ultraviolet because we have church windows that have been there for hundreds of years and they still preserve fantastic colour. So we elected to use stained glass as our sort of colour source for this. We also have a few other sort of auxiliary items, so these are known as the PanCam small items collectively. So there's some fiducial markers. Now these are for allowing us to sort of check the geometric calibration of the camera when we get there. The last item we have here is a rover inspection mirror. So it's a small convex mirror. By pointing PanCam down at this little convex mirror, we can actually see underneath the rover.
It takes you about 6 months from start to finish to make one, because of all the subcontractors it has to go through, post-processing, and at any point you can scrap it.
So a lot of the parts start off at really heavy aluminium structures, and we're trying to whittle them away to almost nothing so they can fly, so they're nice and light.
Sending things into space is expensive, so a satellite, normal satellite, you try to make everything as light as you can. Of course, with Mars, you've also got to worry about getting back into a planet.
So the landing, it's what they call the 7 minutes of terror as you go down through the atmosphere of Mars. That involves, first of all, a heat shield. It's a very thin atmosphere, so to slow it down further, you need parachutes. So there's a succession of parachutes. And then there's something called the landed platform and the descent module, which is outside that. So that has retro rockets, which fire towards Mars to slow it down later in its descent, so it doesn't actually hit the surface very hard.
So weight is pretty critical.
What we do is we machine it as a block with all of this still solid in the centre.
A lot of the parts involve making lots of various jigs and fixtures to actually hold the part, so you can actually make it to what the designer wanted to start with.
We used standard CNC machining.
It's a 4-axis CNC machine with 12 tools that automatically change once you've programmed it.
Which involves lots of number crunching.
There's more to it than just putting the piece of metal in and press go.
And most of the machining was done here.
Then we use a process called wire cutting.
It cuts through metal through use of electrical discharge.
So just a wire moves around, cutting out that profile. Then we machine the bottom separately, which is quite similar to that piece. The lid, of course, is held down by screws and has a radio frequency seal on it to make sure that we don't get any interference. But that's welded in, stress relieved, and then machined back. Then it's painted with very special space qualified paint inside and out to give us a final product. As well as the structure, MSSL provides the interface electronics.
The PAU design is basically a central point to control all cameras.
And the power electronics, which is contained in this box at the front.
Which does convert from the rover power supply to the regulated power supplies to the rest of the electronics.
This is a copy of the field programmable gate array, which is used on PanCam. It's got 256 legs, so we have to degold, pre-tin and bend these to give us a leg, what we call a gull wing leg, which is basically like an S-shape. That allows us to solder it on the board. Unfortunately, these are very expensive, as they always are for anything to do with ESA acceptable components. Lots of money.
The main challenge is really the temperature.
The thermal environment on Mars is very harsh. So so on a good day it might be 0 to 5 degrees centigrade, something like that, on the sunlit side. But at night, every night, it gets down to minus 100 to minus 120 degrees centigrade.
Well, the difficulty with this extreme temperature range is the thermal expansion and contraction.
You know, the PCB is expanding and contracting over a temperature range, and your components, especially if it's ceramic, and a lot of them are, that doesn't move much. So you have a board that's moving with a component sitting on it that isn't moving, and obviously something has to give, and that's usually the solder joint.
In the mission there's always various models.
There was the flight model, the engineering model and the test model. There might have been about 6 or 7 various different types of models, and then the pre-flight model.
This unit itself is it's the life test model for the structure.
This model goes through everything in accelerated, everything what that PanCam is going to go through, so the vibration of the rocket launch, the shock of the staging, and then the fluctuation in temperature. And we want to make sure that the hardware can resist multiple days on Mars because you want it to last. And it has been useful because there's been hardware that has failed and required redesign and retesting, and then was a success. The biggest thing, the most expensive and time-consuming thing, and the hardest to get used to is the planetary protection.
Because the ExoMars rover will be actually landing on Mars, we need to keep it biologically clean because we can't contaminate the surface with Earth-based biology, as well as it would create potential false positives when we're actually looking for life on Mars. A clean room under planetary protection measures is cleaner than an operating theatre. Anytime you're in the ISO 5 clean room, you've got to be thinking about what you're touching. You have to stand in such a way.
You have to change your gloves as soon as you touch something that's not considered clean. You have to know what is clean, what isn't. You need to have someone working with you that's you label as a dirty buddy because they will be handling stuff that you shouldn't handle. Every time someone goes in, they need an observer.
It's a daily battle against bacteria, really. Once the lid's on and it's ready to go, we take biological assays and then we send that off for testing. They then incubate those samples, grow, see if anything grows, and then they'll count the number of colonies essentially formed. And we're aiming for 0, and that's generally what we get. If it comes back with a higher number, we then have to re-clean and re-assay.
On the software side, we are doing what we call the ground support. We're also doing the software simulation, so allow the European agency to basically integrate our hardware to the rover. We already delivered the hardware, so it is now in Stevenage in Airbus. Now they're putting all the things on the rover, and we will expect that after 9 months, fly to Mars, so we should be able to see our images. And when the image come back, we also have a team in here to processing those images. At the moment, the software I'm writing now, we have a supercomputer ready in here, so allow us to actually processing all the 3D images.
It's such a difference to see images from a satellite, from orbit, or actually to have images and data sets from the surface directly. So you feel a little bit like you are on the surface yourself. That's at least my impression. So this rover is kind of a robotic field geologist, and I'm on board.
It's been a really, really exciting project. If you told me 10 years ago I'd be working on a mission go to space at all, let alone making hardware that went to Mars, I wouldn't have believed you.
A mission landing on another planet makes me dream more than a mission that's in orbit or just in space. It's a bit more. I don't know, when you talk to someone and you say I'm working on a mission that's landing on Mars, it talks to people.
Anybody that goes out and looks at the sky at night and you see maybe a few thousand stars, and just looking at that, I think everybody thinks there must be the possibility of having life somewhere else. There's a quest for sort of knowing whether we really are alone or not.